Okay, so security basically means the system can meet all the reliability standards. If the standard change, the boundary of stability, security also change. But for any system which is well designed and also the reliability standards are reasonable, usually security need to a smaller concept than the stability, which means any secure system has to be stable, right? But there could be cases if some new equipment are placed on the power system, and the engineer have not fully understand this new equipment, such as like inverter-based renewable resources. They need to do a more stability study. So it could be possible, but even that's not very often. If this new equipment can cause some new stability issues, but which is not fully understood, which means if they operate this equipment based on existing reliability standard, they may think this situation is secure, but actually instability may happen. But usually, secure system have to be stable, okay? An oscillatory system doesn't mean the system has to be either unstable or insecure. It just means there's some phenomenon showing some operating quantity changing periodically. Yeah, so if the system is oscillating, as long as there's enough damping, the system oscillation will decrease and eventually will go back to the new equilibrium. So the blue sentences give you some examples, such as unstable system is insecure, but stable system may also be insecure if some operating quantity violate their standards. For oscillatory system, it can be either secure or insecure, or stable or unstable, depending on the so what happened on the system. Let's talk more about the power system operations. So for a real power system, it can operate in the normal condition, which means nothing happened and the system is secure enough. By being secure enough, I mean it's secure. It meets all the standards, and also it has sufficient margin away from the boundary of reliability. So even you have a contingency happening on the system is still secure. It still meets all the standard. For instance, maybe the system has two areas, and one area sending power to the other area, but there are many transmission lines. So even you open one line, which is considered a -1 contingency, the remaining line has enough margin to deliver the power. So the system is very secure. So that considered as normal condition, so which is the green bubble. But for some cases, if the system right now doesn't violate any standard, but you can predict if next contingency happen, some equipment will have violations, like maybe voltage become lower than the limit or higher than the limit, or some line can be overloaded, but that has not happened yet. But for the next contingency, very likely the system will become insecure. So that is considered alert state. Alert state basically is still normal, but it doesn't have enough safety margin for system to withstand a next contingency. Example could be, it can be, right now it's in the N-1 condition, no violation, but if you add another contingency become N-1 minus 1, then the system will become insecure. So system is secure in terms of N-1, but not secure in terms of N-2 or N-3 or more. If that happens, the operator need to take a preventive control actions. Preventive control action means you don't have to, right? You can take the risk, okay? Because any control action will come with some price. There's no free control. So when you do the control, you may lose some capability for, or you may sacrifice some economical things. So if you want to pay the price, then then you need to take controls. That will bring system back to normal to increase the margin against any violation. But if you want to take this risk, you can do nothing, right? You can just stay there and wait. Maybe the system will increase the margin like on its own. For instance, if the load decline, right now your operating system during the peak hours, the load is very high, like 4 p.m. And you, based on your calculations, so if this line is open, the neighboring area will have lower voltage and other lines will be overloaded. But you just cross your finger to think maybe next hour the load declined, my system will be fine. So you don't have to do anything. But if you want to do something, that's called preventive control. So both normal state and alert state will be considered normal operating conditions. And then the other bubble just indicate more complex situations. So for instance, there's some emergency state, extreme state, restorative state. So there will be transitions between any two states. So any red transition indicates something happened, bad thing happened. And the blue transition means some contraction, a good thing to happen, okay? So we can go into more details on those transitions. So the operator need to make sure they have the full picture of this diagram and know exactly where the current system is located by collecting all the data. So they try to avoid this one, the extreme state. Extreme state basically means you just lose all the control. You just wait until system to have blackout, cascading outages until everything is over. Then you take a very long process to bring the system back by the restorative control. The restorative control can take many hours or several days, right? So that's definitely, if you avoid this one from happening, so you always make sure the system is changing among the normal state, alert state, and sometimes emergency state. Even emergency state, as long as it doesn't damage anything, it's still okay. So this is the number one thing for operator to avoid, right? Never make a system enter this state. So that's basically equivalent to power outages and blackouts. And because that, once the system enters that state, it's out of your control. Okay, then you need to design your reliability criteria or standard to make sure if the system enters alert state, it can go back, or at least it doesn't go to emergency state. Okay, emergency state compared to alert state, which means the system is insecure. It's insecure. Being insecure means some reliability standards have been violated. For instance, if you want the substation operating at 500 kV, the voltage above maybe 98% or 95%. But right now, after something happened, the voltage go to 94.5%. It's slightly under the threshold, but it doesn't damage any equipment, but it just violates the standard you develop. So if violation already happened, so you're pretty sure the system have entered the emergency state, then at this state, you need to take corrective actions. So it's different from preventive action. Corrective action means you have to take action. There's no reason to wait. You take whatever control action you're available immediately, right? There's no delay. As long as you are sure the system is in emergency state, you need to take this control action. The control action is such as if some devices have lower voltage that can damage that device, you need to trip that device. You can open the line and trip a generator. If like one generator operating at frequency very low, so there will be a local protection to trip that generator. All the protections or remedial actions are considered corrective control. In terms of the terminologies, sometimes when the engineer says protective actions, some engineers say remedial actions, remedial control actions. Usually protective action means protecting an individual equipment. And remedial control actions means protecting one area of system. It's like wider area protection. But anyway, both actions are considered corrective actions. So corrective actions, there's no wait. As long as you know the state, you have to take immediately. So you hope this control action can be very effective and to bring the system back to the normal condition. So that's great. But also, sometimes it's also acceptable if you only bring the system back to alert state. Because once it enters alert state, there's no violation anymore. So it give you longer time. Maybe the load will decline, so the system become normal. Or you can take a further preventive action back. Okay, so if the corrective control it failed, it didn't take control action timely, the system may enter may go to the extreme condition, which means system will collapse. Then you need to bring the system back, right? You take a restorative control, or another option is you can do a more aggressive control, such as I know the failure is propagating in this area. There's no way I can just clear all the failure. I just cut off this area to make it be an island. Then the rest of system will be protected. So that can be considered some emergency control. Emergency control means economical factors were not important anymore. So you have to save the system as much as you can. Okay, you can take any action. If you don't take action, that's violating the reliability standard. So that's another more aggressive control. Okay, corrective control is still focusing on protecting either one equipment or one area. So there's not a large influence on the load or the system operating. But emergency control, you can just do load shedding. You just trip all the generator or load in one area to protect rest of system. That's fine. Then your system will go back to restorative state. Restorative state means the system is not integrated anymore. It can have many pieces running in parallel. Then you need to bring the system back, and eventually we'll go back to normal. Okay, so that's a very important diagram to show what operator is operating. Look at the system as and how the operator can operate the system among different situations. So reliability standards designed by the plant engineer and used by the operator, they need to make sure all frequently occurring contingencies such as MS1, MS2, they won't bring the system to the emergency or extreme state. So the system only operate between the normal state and the alert state sometimes. Okay, so when system enters the alert state, the operator need to take action to bring the system back, or they want to take the risk to wait until system go back. If the violation is not, if there's no violation and the margin is still not very small. Any question on this diagram? Okay. So in the rest of this course, you keep this diagram in your mind, because sometimes we always need to discuss about the modeling for some specific equipment, like with generator or with transmission line. And even sometime I say, okay, so we can do voltage control, we can do frequency control, but I may ask a question, which type of control in which type of control we can utilize this equipment. Okay, for instance, the exciter, which can change the field voltage or field current of the generator, that can participate in voltage control. So that voltage control can contribute to maybe the preventive control for some situations, and corrective control, and also emergency control. So it can contribute to many things, but some other control focusing on just one type of control. Okay, so in the rest of the course will talk about we'll focus on the three sections. The first section is we're going to model the generator and the load. Okay, so this is the full structure of AC power system with all elements we're going to talk about. So this is the center, right? Center of the structure, which is generator. So in the next session, we'll do the modeling for the generator, the signal generator, from the principle, the detailed circuit, and develop reduced equivalent circuit, and we come up with some equations. So we can use the equation for a dynamic stability study. And we also talk about the load, briefly talk about the load of the generator, how we can model the load, whether it's like a dynamic load or a static load. So we'll cover both. In the second part, we'll focus on modeling these two blocks and the related frequency and voltage control. Okay. So this part is just the prime mover and the control, including the turbine and the governor models. We'll model those elements in detail, and then we talk about how to do the load frequency control from the system-wide. So that's a frequency regulation section. And next, we'll talk about the modeling for the excitation and control system, which is related to automatic voltage regulator connected to the generator. And we also talk about how to utilize transmission system, including some shunt capacitors, reactors, or series capacitor reactors, and other like HVDC and other equipment, power electronic based equipment to do the voltage control. Okay, so that's next two sections. So after that, we'll talk in more details of each individual stability problem. So here I will show a big picture about power system stability. So after we know the models for generator and for its controller, including the governor and the exciters and other control element, so we can have all equations about the generator and the load and the network into this whole set of equations. Because we're going to cover dynamics of the generators, controllers, and also the network. So there will be, most of the equation will be differential equation. So even you think about transmission lines, so transmission lines have inductors, which indulgence, and also the capacitance, right? So which means the voltage and current. If we talk about instantaneous voltage and current, they can be state variables and changing following the electromagnetic dynamics. So basically, if you want to have very accurate models, you have a full set of ordinary differential equations. So I use X here to represent the slow dynamics, focusing on the electromechanical behaviors of generators. So usually that time frame will be from maybe tens of a millisecond to several seconds. And also there's a faster dynamics, mainly focusing on the electromagnetic transient, such as instantaneous voltage, instantaneous current of the network, and also some instantaneous variables inside of the generator and controllers. So those are the fast state. So epsilon here, you just try to say, their average time constant is much smaller. So if you treat like if we consider like per unit value, we treat the time constant with the first set of equation about X has around 1. And the second set of differential equation will have epsilon, which is much smaller than 1, maybe a thousandth or hundreds times smaller. And usually this model will have this structure in 2 time scales, including the electromechanical dynamic and the electromagnetic transient dynamic. So that's the most accurate power system model we have. But that model is too detailed, because when we study the power system stability, instead of looking into how the waveform of voltage, the current can change right after any fault, if we focus on the system behavior, we definitely don't need to use this accurate model. It can be huge. If you think about how many generators you have and how many lines, each line will have instantaneous current voltage to be modeled for dynamic. This is too detailed. So in this course, we'll focus on the next model, reduced model. So we reduced the fast dynamic, such as electromagnetic transient. So we simply treat this part be zero, because that's much smaller than the change in terms of the magnitude compared to the state variable about generator. So we basically make the second side of a differential equation be algebraic equation. So X here means the state variables mainly with generator. Y here means a regional state variable such as instantaneous voltage current in the network or the detail controller. But here, Y is not a state variable anymore. It becomes like algebraic variable. Okay, so if you're not familiar with the differential algebraic equation, this is very challenging equation to either simulate analysis compared to alternate differential equation, because this algebraic equation always need to be true. Okay, so to power system, this is mainly about the power flow in the network. So we ignore the instantaneous dynamics in voltage current of the network. We just treat voltage current as algebraic variable. So we ignore dynamic, which means they can change. Any voltage current can change instantaneously in this model. Then for this model, we want to study stability. So when we talk about stability, we refer to a specific maybe equilibrium of the system. So to find equilibrium, we just simply solve the algebraic part of the equation. Basically, you make the left-hand side both be zero. So that will give you the algebraic equation. So if you can find any solution satisfying those equations, they will give you equilibrium points. It can be a single point or multiple points. Some points are stable, some unstable. Okay, so that is the problem the transient stability analysis is going to address. So there are some goals for transient stability analysis. First, you need to find the domain abstraction of each equilibrium. So if you solve those equations and find a number of solutions for each solution, you need to explore the neighborhood surrounding that equilibrium to see, okay, in this region, the system will keep its stability. So that's called domain abstraction. And if there's such a domain abstraction, you need to evaluate how large this domain abstraction is. So that is about the stability margin. So if you operate at the equilibrium point and there's a boundary surrounding the equilibrium, you need to know how large this region is. That is the margin. That gives you a very simple example. This is just the dynamics about a single synchronous generator connected to infinity bus. So you only have just two state variables. One is the speed, the other is angle for this generator. So if we draw the system dynamic, the phase trajectory about the angle and the speed, so each blue trajectory indicate if you start from that point of state space, how it's going to move. So you see there's a number of green points which indicate stable equilibrium points. And also the red points indicate unstable equilibrium points. So if you start from here, for instance, so after disturbance, your system state will move to this point, it will follow this trajectory, right? It'll go back to a stable equilibrium point. Then you know the system is stable. But if you start from here, that's unstable equilibrium point, the system will either go this way, right? And or go this way. Oh, I need to draw the opposite. Let me draw again. So if you start from this point, because the trajectory always is always moving clockwise. Yeah, clockwise. So it either move this way to become unstable. Let's see. Yeah. Right. So or yeah, that's because from this side it will be yes. So basically just form unstable. If you start from this point, it will follow this trajectory. Right. Eventually it may go to a stable, unstable, but you need to to judge the stability of trajectory, the method is you identify one stable equilibrium point. The most likely your system will go to there. And surrounding this point, you draw a domain of attraction, which could be this region. So domain of attraction means any point starting inside of this domain will always go back to this stable equilibrium point. So this will be the safe region. Okay, so if the system stay in this region, it's stable. Outside of this region, it can be either stable or unstable, depending on eventually where that trajectory goes. So that's a transient stability analysis going to solve. So you could simulate the system trajectory and visualize in this plot, then you will know which one is stable, or there may be some other analytical method. You don't have to know the accurate trajectory, but you can compare the initial energy and the maximum energy for the boundary of the domain of attraction, then compare. Okay, so if your initial energy is bigger, you will escape from this domain. There could be different methods to solve this problem. So that will be the section of transient stability going to address. But sometimes if you're pretty sure my system will not be unstable, it will always move around that one of the green point, which is stable equilibrium. Then you don't have to solve the entire differential equation as a nonlinear model. You can linearize the system. You give which equilibrium you want to operate the system, and you replace the system state by the equilibrium plus some maybe a little variation, very small. Then you plug into the differential equation and linearize the equation by Taylor expansion. So basically, you only just find the first order derivative, very similar to the Newton-Raphson approach when you solve Prof law. You do the Taylor expansion, but you only just find the first order, and you calculate the Jacobian. Okay, so finally, the A will basically represent the Jacobian matrix of the regional dynamic model. So now you have a linear model. You have so X here is a state variables about generator and controller, and A here is just a linear matrix, constant. So to answer the stability for this system, you want to know if the system is oscillating, whether oscillation will be growing or declining, whether damping will be positive or negative. To answer that question, we're going to utilize a small signal stability analysis technique. So we'll identify oscillation mode and also figure out the damping. One approach to answer such questions will be finding the eigenvalues for A. So A is a square matrix. You first diagonalize the square matrix by transformation, and the diagonal element will give you eigenvalue. So if the system is oscillatory, it will have at least one pair of conjugated eigenvalues, such as this one. So it will be on the left-hand side. If it's the pair of eigenvalue on the left-hand side of complex plane, the system is stable. If all eigenvalue on left-hand side of plane, the system will be stable in the small signal stability point of view. If any eigenvalue is on the right-hand side, the system will be unstable. So X will be about damping and Y about the frequency. So if it becomes very close to the real axis, the omega will be small, and the system will have a very slow oscillation. If the omega is big, so it's far from the real axis, so it will have fast oscillation. So if it's far away from the y-axis, which is imaginary axis, the damping will be large enough. Okay, system will be stable. So that's a small signal stability analysis going to solve in that section. So we'll have that section to talk in more details about the measures. Another possibility is, your system won't oscillate. Okay, my system, even it may have some a little bit oscillatory behavior, but that's not the cause any like small signal stability or any big problem. Then you can focus. You don't have to keep the dynamic. You can even reduce the dynamic. you only focus on your analysis on the result in the algebra equation. You see, you ignore both dynamic in either slow or fast time scale. Then for this set of algebra equation, you will study the nature of each equilibrium. So some equilibrium may be stable, some will be unstable. If all equilibrium are stable, you won't lose stability, but that usually each stable equilibrium will be surrounded by many unstable equilibrium. Then you focus on this set of equation and you keep a state variable, some state variable of generator, and for the non-state variable like voltage or current, you can focus on some of the operating quantities, such as some voltages and some current. By current, you can replace current by the power. So you have set equation focusing on how the voltage can change with power under different system states. So this specific problem is called voltage stability problem, and mathematically speaking, is related to one type of a problem on bifurcation. So for this problem, you will study how the stable equilibrium point related to another unstable equilibrium point. So you see, this is stable equilibrium point, which means if there's a boundary on this side, it will be domain of traction, right? So if the system always stay inside of this domain of traction, is stable from the transient stability point of view. But if the load increase, so if the load increase and the system, if this load increase, that make the distance to the boundary or to the unstable equilibrium become shorter, and eventually they can merge to the same equilibrium, but that's unstable. Why? Because from this side, so if you start from this side, it will move away from this boundary. And if you come from this side, it will come to this equilibrium. So eventually, any trajectory starting in the space will not go to a stable equilibrium. So this become unstable. So if such, they change from the left figure to right figure happen either gradually or suddenly, so that is considered bifurcation. It just disappear. It's just disappearing of the stable equilibrium. So this is called the voltage stability. So we'll answer some questions about this voltage stability in the last section of this course. Okay, so you have now a big picture on what we're going to do in the rest of this course. So we first talk about modeling, including generator, load, controllers, then we move to each specific stability problem. So we focus on the transient stability, which is a nonlinear dynamic problem, a small signal stability on linear dynamic problem, and voltage stability on the bifurcation problem. Any question? It's very informative, but don't worry. At the end of this course, you will have much better ideas about the modeling and also stability problem. Next few slides, let's talk a little bit more, and I can give you some example of those stability problems, because this slide is very mathematical. Right? So we'll come to some real examples. This slide will talk about some classifications. We already mentioned the transient stability, voltage stability, and small signal stability. But I will talk more about from the different perspective on how to categorize the stability problem. Power system stability is essentially just single nonlinear system stability problem, which means if you have really powerful tool, you can just study this system, right? You don't have to reduce any equation. And if you have a also powerful tool, you can study this problem, you can stay there. You don't, because once you know the stability of this system or that system, you know exactly what's going to happen from maybe small signal perspective or voltage perspective. But just because of we don't have so powerful tools, sometimes we have to focus on a smaller system or reduced system by assuming maybe some of the variables can be ignored. That's why it's still valuable to categorize the main causes of the instability. Then we need to do some classification. So just because the dimension and the complexity of the system is really high. So if we can focus on specific problem based on the phenomenon, we can select an appropriate analytical technique. Then we need to consider some key factors which can help us to classify those problems. Okay. So there are different methods to classify power system stability problem. We can use the physical nature of the phenomenon or the modes of the instability, such as if instability happens, it first appear on angle, frequency, or voltage. So we can just use those three factors to categorize the problem. Okay. Another idea is usually the instability, if instability issue happen, it's not caused in normal condition. It has to be caused by some disturbance. So disturbance can be small or large. So we can use the size of disturbance to classify the stability problem. There also another idea is depend on what device is, what the process is, and also time scale. So we can, if we consider those factors, we can categorize stability problem. Okay, such as there could be some stability problem mainly happen in the transient period within 10 seconds, or maybe short term, maybe a few seconds. Some will happen from 10 seconds to several minutes, so we call it midterm problem. And some stability problem really need to take a long enough time, from tenths of second to tenths of minutes. So we call such problem as long-term problem. Then let's use those three ideas, try to see how many specific stability problem we can generate. So we start from the power system stability as the integrated problem. From the first dimension, we study rod angle stability, frequency stability, and voltage stability. Okay. In the second dimension, we consider small versus large disturbance. So we can have a small disturbance angle stability, this is a large disturbance angle stability. We call it typically transient stability. Then we can have large disturbance voltage stability and small disturbance voltage stability. And from the time scale, we can have a short-term stability. We have either short-term or long-term, short-term and long-term, right? So we use three dimensions to create finally a number of highlighted boxes for specific measures or tools to solve. You may feel some boxes may be missing, right? For the frequency stability, we didn't talk about either like a small disturbance or large disturbance, because in the modern power system, some problems they are not very often, so we don't have to categorize the problem at that dimension. We only focus on maybe short-term and long-term. And another example is for rod angle stability. You see, we only focus on short-term because from long-term, such stability may be addressed by another analysis, like for instance, by voltage stability. So we don't have to, or by frequency stability, we don't have to study long-term angle stability problem. The bottom figure gives you some examples. The first one indicate the line flow of a power system is oscillating. It starts from this time, and you see the envelope stay about the same, at least not decaying, which means the system has sustained oscillations. So damping can be either negative or very small. It's not large enough. So this is a typical example for small disturbance angle stability. Okay. The second, you have many generators in the system, but after disturbance, one group of generators are flying away from the rest of the system. So this is a typical example of a transient instability. And the third one, you see this is voltage at one substation around the 230 kV. So after a number of events, the voltage can go up, go down, but it always stay around the nominal voltage, but suddenly drop to very low value. So this phenomenon is called voltage collapse. So that's a typical example for voltage stability. And if you want to figure out is either large disturbance or small disturbance, at the beginning, we may have some phenomenon which can be studied as large disturbance, and at also some stage more like a small disturbance. So it may be both. Okay. All right. So next slide, we talk about the more about the rotor angle stability. Rotor angle stability, maybe we sometimes we also call it angular stability. It just means the stability of the similar generators of the power system to return the synchronism following either large disturbance or small disturbance. So if you focus on large disturbance, that's called transient stability. If you focus on small disturbance, that's called small signal or small disturbance angle stability. The phenomenon basically just there's angular swings of the rotors of generators, and if you don't do any control, some generator will become out of step against the rest of the system. So such phenomenon is called loss of synchronism. So one example could be this is a model of the Northeastern power system. It has 3 groups of generators. So each group will tend to become coherent following any disturbance, which means the generator inside of each circle, they try to stay together. But if you have some disturbance, the 3 groups of generators may oscillate against each other. There are 2 scenarios. The first one is this black group speed up and become divergent from the rest of the system. And the second scenario is this blue group, which basically about 1 power plant in Canada, they're flying away from the rest of the system. So both scenarios considered rotor angle instabilities. If you read some literatures, especially published maybe 20 or 30 years ago, and some paper talk about dynamic stability. Dynamic stability is a literal term in some other field, like a control system and control. But in power system, that's not a good term, okay, for power system papers and report, because it can be confusing. In North America, dynamic stability mainly talk about small signal stability. In Europe, if you see the dynamic stability, people really mean transient stability. So it can be very confusing. So the IEEE and the CGRIP, they both recommend not using this term in the paper or report. Okay, let's finish this slide. So here is just a rotor driven by a steam turbine. So the rotor, the dynamics, if it's at any equilibrium, that will means there's some input torque from the turbine. So from the thermal turbine or hydro turbine, but basically this generator is more likely a round rotor generator from steam turbine. And also there's another torque, electric torque. This electric torque depends on the load of the generator. Okay. So that electric torque is proportional to the power, the active power the generator delivers to the power system. So usually those 2 torques have to be equal because their difference, if they have any non-zero difference, that difference will define accelerating torque. So that accelerating torque will speed up the rotor. But if you want all the generators operate at 60 Hertz, this one has to be 0, right? Even it may be temporarily positive or negative, but it cannot last for a long time. If that happens, that will explain why some of generator will speed up, because their accelerating torque are positive over extended period. So that will make a generator be unstable. So the rotor angle stability is mainly just maintain the balance between the mechanical input torque and the electric output torque. Mechanical input torque, this is the TIM, can be controlled by governor. Okay, this is the operator or the engineer, they can control or design control strategy. But the electric torque really depends on the loading or the contingencies of the system, because you cannot predict what's going to happen. If you have a short circuit fault, that will suddenly reduce the electric torque. And if you don't take action, you don't reduce the mechanical torque, the accelerating torque will go up, the system will become unstable. Okay, so then I will come with this question. So if I'm the operator operating a single cylinder generator, and I connect this generator to a load, I don't know too much about the load. So the load can be purely resistive load. For instance, this generator is a diesel generator, it just power my house. My house is pretty much resistive load. It can be powering another motor, which can be another cylinder generator. It just behave like a motor or pump. So is the transient stability a concern to me for both cases? Do I need to worry about transient stability? Let's see for the first scenario. Do we need to worry about transient stability? Is this generator going to become transient unstable? No. Okay. So if this generator has positive accelerating torque, it will speed up. If I set it to operate at 60 Hertz, if it speed up, it can operate at 61 Hertz, 62 Hertz. It doesn't matter as long as my load can take that high frequency. That's usually the case. So if you have any experience to have a backup generator for your house, it could be a diesel generator, a cylinder generator to power your house. If like the winter storm come and you lose the electricity, use a diesel generator to power your house. If you definitely your house has some washer dryer with a motor, but they assume you don't use a washer and dryer, just heater. It doesn't really matter. The electricity is 60 Hertz, 50 Hertz, 61, 62, right? So such system has no transient stability concern. It's not, you don't worry, there's no transient stability, because transient stability means the synchronism. To make a system be synchronized, you have to have at least two rotational mass, right? A component carrying mass. Then they will move together at same speed. So only the second case will have transient stability concern, which means you do need to have two machines. They're both synchronous machines. So for a simple power system with just single generator connected to a load, only when the load side include rotating mass. So then it can provide a reference against which loss of synchronism will become concern. Okay. Yeah. So this is the last slide. So we have a few more slides to finish. 3 more slides, so we can cover on next Monday. So because the windstorm will come this weekend, so I will send notice if we cannot, if the campus is closed, we'll do a Zoom meeting for the class. All right.